Ladies and gentlemen, hello and welcome. Coming to you once again, not quite live, from One Take Studios, where we are looking at the idea of testing a proportion today. So testing a proportion P. P is the variable that goes with proportion. This is very similar to testing mu, which my previous two videos have been about. So this is not meant to be a from-scratch explanation of things. So if there's concepts that you feel like you're missing after viewing this, go back to the last two videos, which are introductions to statistical tests and then testing a mean mu. So today we're testing a proportion P and just a reminder of what it means if we have P. I'm going to go this far right here. There we go. All right, so we are now talking about something that is binomial. So success and failure and the proportions thereof. R is the number of successes, not a hashtag, number of successes, and N is the number of trials. This is a review. P hat is what we use for an estimate for P. Just like we were using X bar to estimate mu, P hat goes in place of P. We get that estimate by dividing the number of successes by the number of trials, so R over N. Alright, so all of that is just a review. NP and NQ must both be greater than 5 in order for us to proceed with our test. Again, why is this? If this is true, we are indicating a distribution of data that is normal. And if the data is a normal distribution, it becomes predictable so that we can actually draw conclusions, make assumptions that have some sort of value to them. Alright, so that's going to be an important kickstarter then for getting the entire process going. As far as the null hypothesis, we still have a null hypothesis. Notice our changes though. So this is H sub 0 again, 0 indicating our starting hypothesis. Instead of having mu is equal to k, which is some number, we have p is equal to k, which is still some number. So we are swapping out mu and replacing it with p. That means that for my alternate hypotheses, it is going to be one of these three, not all of the above. But again, the notation H sub 1, this is the first hypothesis after that one, so H sub 1. And we are either going to choose P is less than K, which would be left-tailed, P is greater than K, which would be right-tailed, or P is not equal to K, which would be two-tailed. So again, just taking out mu, replacing it with P. A couple of formulas that you may or may not need depending on what it is that you've got going on. If you intend to be doing this with some table work, you're probably going to need to know sigma, so this is our formula there, the square root of PQ over N, so that's if you need to find a standard deviation, and if you need a z-score, it's going to be P hat minus P instead of X bar minus X over the standard deviation, which we just said right here is the square root of PQ over N. So this fits the model of other things that we've used, but if we're using the calculator, we're not going to need to see much of either one of these two. I want to spend most of our time, again, running you through a problem because I think this is easiest to see if you can actually see it in action. Alright, so I did a little bit of research. What I have scribbled in my margin here is EduCause. So there was an EduCause survey that I found on the internet that says that 30% of students prefer online learning. And 70% would rather be in the classroom in some format or another. So if 30% of students prefer online learning, based on the EduCause survey, I did some surveying of myself, and I talked to 36 of my students today, and 7 of those 36 say that they prefer online learning. So 7 out of 36 is actually less than 30%, so my question is, if I test this, is this sample an indication that the proportion of students at my school is less than 30%? Keep in mind, I have 36 students speaking for the entire student body, so I'm trying to decide if that's different enough from the 30% to say that, hey, my school is not the same as the national average. Let's find out, shall we? Alpha we're going to use at 5%. All right, so that is our level of significance. So things that we know, level of significance is already listed, so I'm just going to leave it there. I also know that, let's see here, H sub O, my null hypothesis for this thing, again, is that P is something. Well, what is it? 30%, perhaps, 30%, there we go. What is my alternate? My alternate hypothesis is again going to be P, but we're looking at, is it less than? So it's less than 30% based on the words that we are using here to spur us on. So we've got our hypotheses, we've got this. What else do we need to know? We're going to want to have our distribution. Ooh, distribution. What kind of distribution is this? It doesn't say if it's normal or not. Is it normal? Could it be normal? Let's find out. We said that NP and NQ have to be greater than 5, yes? So NP, probability of success, 30%. N, 30. So what is 36 times 30%? Borrowing my calculator real quick here. Oops, or not. 30% of 36 is 10.8, which you may or may not be able to see. Is 10.8 larger than 5? Yup. What if I do my 70% times 36? So now I'm doing NQ. Technically it's QN the way I typed it in, but is that also greater than 5? Oh look, NP and NQ are both greater than 5 at 10.8 and 25.2. Therefore, I can say that this is a normal distribution. Normal distribution. Excellent. So, if I do intend to do most of my calculating in a calculator, let us pull up that screen instead. Switching, this one right here. There we go. All right. So what will we be looking for this time? Again, everything fun and exciting is on the menu. There we are. And we are still in the world of statistics. And recently we've been talking about stat tests, which is number 7. So I'm going to go there. What am I going to pick, though? We've talked about the z-test if we happen to know what sigma is. We've talked about the t-test if we don't know what sigma is, but we have s instead. This we've said is normal, so a z-test kind of makes sense, but we're doing proportions, so right here, ladies and gents, we are looking at the one-prop z-test. For proportions, based on the fact that we have the z here, this is still going to be a normal distribution. All right, so what are they asking for? This is the original value, this is the null hypothesis, and that p has a value of 0.3. So there's my 30%. My number of successes was 7, so we'll get that in there. And my number of total students surveyed, total number of trials there is 36. And we are trying to indicate, is this less than? That's going to be this guy right here. And let her run. Again, we're seeing something similar to what we've seen before. So what am I jotting down right now? Important information like my sample test statistic, one of them at least, is that I have a z-score of negative 1.38. So I am writing that down. And I also have a p-value of 0.083. I'm going to round it there, I think. P-hat, I'm not going to write that down, although I could. That's 19%, which we've said is less than the 30% standard, and we already know our sample size was 36 for that. All right, so let's flip back to the other screen again then. Eeny, meeny, miny, there's Mo. All right, so jotted down the information that we might need, looking for a sketch of what this would look like. Let's do something like this. There we go, and here we go. And I'm going to go with my z-scores, so I'm going to put 0 in the middle. And I know that negative 1.38 is the z-score associated with my information. So let's call this negative 1, and let's call this negative 2. Is this drawn to scale? Goodness gracious, no. We can deal with that, though. All right, so negative 1.38. That's going to be roughly about here-ish, something like that. Okay, so that is the negative 1.38. That's how I know where this goes. And we're talking less than left-tailed, so my sketch is going to be this piece right here. So what I'm saying is that this line right here is at my z-score of the negative 1.38. And this shaded area is the p-value, which is 0.083. So we're saying that's roughly 8% of my area, but what this also means is that the probability of me getting 7 out of 36, if 30% is the true population proportion, the probability of that happening accidentally is at about 8. Again, our decision is made in the same way. We want to compare the p-value to the alpha value. And if I'm looking at this, I am seeing that yes, 0.08, which is a little bit over 8%, is definitely larger than the 5%. What does it mean if my p-value is larger than alpha? Remember, for this, it's kind of backwards in our brains. We are programmed to think that things that are big are significant. In this case, we're looking for things that are really unlikely. Really tiny probabilities are significant. So is 8% really tiny? No, it's bigger than 5%. This is not significant. So I am not going to reject the norm. I'm going to say that this data is not convincing enough to make me walk away from the 30%. How might I write that? Oh, let's see. Let's see if I can squeeze this in here, I guess. At the 5% level of significance, I'm going to abbreviate that as SIG, the data is not significant. All right, it's too big to be significant. Is not significant enough to reject. What is it that we are not? So we are not rejecting. What are we not rejecting? We are not rejecting the null hypothesis, the 30%. So it's not significant enough to reject that 30% of students prefer online learning. And again, be careful with your wording here. All right, so because this is larger, tiny things are significant in this particular world that we're living in. All right, this is larger, so it is not significant enough to reject. We are not rejecting the 30%. This is not enough of a difference to make that true. Okay. Strong advice, don't do these on your own with no feedback. Please make sure that after you've tried something like this, that you check in with a source that you know is reasonable to find out if you are truly doing this right or if you just think you're doing it right, all right? You don't want to go around feeling that it's okay when it's not actually okay. All right? Have fun. Good luck.